Hello friends, today we will discuss how to calculate structural number of a flexible pavement. Structural number is used as a parameter in the design of flexible pavement by AASHTO method. Based on the design traffic, we calculate what is the required value of structural number, and then structural number is converted into the thickness of the layers. It represents overall structural requirement of a pavement to sustain the design traffic loading. It is given by this equation that Sn is equal to A1 into D1 plus A2 M2 D2 plus A3 into M3 into D3. Here A1, A2, A3, they are structural layer coefficients. This is for bearing course, that is your top layer, bituminous layer. This is for base layer and this is for subbase layer. D1, D2, D3 are their corresponding thicknesses, but in inches. So the thickness D1 is the thickness of asphalt concrete in inch, base material in inch, and sub-base layer in inch. M2 and M3, they are introduced as a drainage coefficients for base layer and sub-base layer respectively. These layer coefficients A1, A2, A3, they represent the strength of the material, and that will depend upon the type of material being used in a layer. For example, if you consider the asphalt layer, coefficient A1. A1 is the layer coefficient for asphalt layer, and its value depends upon the elastic modulus of asphalt layer. This type of relationship is given in AASHTO guide of pavement design, that when you take on x-axis the elastic modulus, E value at 68 degree Fahrenheit, or you can say 20 degrees centigrade, and on y-axis you take the coefficient A1. Now this is the kind of correlation, and this is E value in PSI. All units in AASHTO guide is in FPS system. So for this value, let us say, start with 100,000 and it ends here at 450,000 psi. You can use this chart to get the value of coefficient A1. 1 psi is 0.007 MPa. So when I say 100,000 psi, it means 700 MPa. 700 MPa. Now the second is for sub-base layer. A2 is the layer coefficient for base layer. Base layer can be of a unbound material like granular base layer. It can be a cement treated layer, or it can be bitumen treated layer also. To calculate this value of A2, the guide provides a kind of nomogram, and it suggests use of any of the four property. Either you can use CBR of the base material, you can use R value. R value is also a measure of response of compacted sample of soil or aggregate layer to a vertically applied load, and this is considered to be an alternate of CBR, or it can be as a triaxial test result, or EBS, that is base course layer E value, modulus value. And in the guide there are this type of charts are suggested to calculate the value of A2. This is E base course and this is the Texas triaxial. This is R value and this is a line for CBR. And this is A2, coefficient A2. For 100% CBR, this value of A2 is 0.14. And corresponding to this 100% CBR, R value is around 85. This triaxial test result is around 2 psi and E value is around 30,000 psi. 30,000 psi. These are the values obtained during AASHTO road test. You can determine, depending upon the property of the material, you can use any one of these 4 parameters to determine the A2 coefficient. A2 coefficient can also be determined if you know the value of EBS, and that is 0.249 into log on 10 base EBS minus 0.977. 0.977. So EBS, what guide suggests that should be estimated based on AASHTO method. Now this EBS for aggregate base layer, EBS will be the function of stress state within the layer, theta. That is the normal equation to calculate EBS, K1 theta power K2, where theta is the sum of principal stresses, sigma 1 plus sigma 2 plus sigma 3, and this total is called the stress state. And this K1 and K2, they are coefficients that depend upon the property of the material. The normal range of K1 is 3000 to 8000, and this theta, normal range of theta is 0.5 to 0.7. This depends upon the condition of the layer, moisture condition in the layer. If the layer is in damp condition or in dry condition, damp condition or wet condition, that will decide the value of K1 and theta. If it is in the dry condition, then this is 8000. If it is in wet condition, then its value is around 3000 or maybe 3200. If it is average damp condition, then its value may be around 4000. Value of K2 varies from 0.5 to 0.7. Now, theta will depend upon the stress state, and stress state basically is dependent on the layer, the thickness of asphalt layer, as well as the strength of the subgrade material. More is the thickness of the asphalt layer, means the layer above base course, lesser will be the stress coming on the base. And therefore, a table is suggested in the guide to estimate the value of theta depending upon the thickness of asphalt layer. The asphalt concrete layer thickness is, if it is less than 2 inch, 2 to 4 inch, 4 to 6 inch, and more than 6 inch. And at the same time, what is the reagent modulus or elastic modulus of subgrade soil, road bed material of subgrade? If it is, this is the 3000 psi or 7500 psi, or maybe you can take 15,000 psi, then values of theta are given in this table. It can be 20 here, 25 here, 30 here, and if you go, as the layer thickness increases, the stress coming on the base layer will reduce, and accordingly theta will reduce. So here you can take 5, 5, 5. All these values are given in this table, and you can choose the value of theta, you can choose the value of K1 and K2 depending upon the condition of the moisture in the layer. That is how you can calculate the coefficient, layer coefficient A2. Similarly, the layer coefficient for subbase layer A3 is given by this equation, 0.277 into log of ESB. Now here it is subbase, earlier it was BS, minus 0.829. Now here also this ESB will change the same manner as E value of base layer. So it will depend upon the moisture condition in the layer, it will depend upon the stress condition also. So you can estimate what will be the moisture condition in the field, and accordingly if it is damp condition, then this MR or ESB can be taken as 5400 theta to the power 0.6. Means same value, MR or ESB is K1 into theta power K2. K1 is 5400, K2 0.6. And for wet condition, this can be 4600 theta power 0.6. So this coefficient will reduce if the condition of the layer remains wet for good amount of time in a year. Then the strength will reduce and MR will reduce, and that is ESB is put here, so A3 will also reduce. That is how we calculate A2 and A3. Now for cement treated base and for bitumen treated base, again there is a set of nomograms in the guide, AASHTO guide, to calculate this A2 for cement treated base. Now this is the layer coefficient A2 or A3, and this you can find out either based on UCS, 7-day UCS, or you can find out based on modulus value of cement treated base, modulus value. So here also you have this kind of values on this chart. It varies from, let us say, 5 to more than 10. And here UCS is changing from, now this is into 10 power 5. So when I say 5, it means 500,000. 10 into 10 power minus 10 to the power 5 psi. And similarly, UCS can be 200, 400, or it can be 600, 800, or maybe here 1000. And you can find out what is the value of this coefficient. Let us say 0.15, 0.18, 0.2, and so on. So here you can get a value something like 0.26. So you can calculate the value of A2 or A3 based on UCS or modulus if the layer is cement stabilized. If it is bitumen stabilized, then also a similar kind of monogram is available where you can find out based on either Marshall stability or based on elastic modulus. Once you get the values of layer coefficients, then the next step is to find out the drainage coefficient. all layers below the surface layers are assigned a drainage coefficient M for base as well as for subbase, that is your M2 and M3. And this represents the loss of strength in a layer because of presence of moisture. How much time it remains in the contact of the water in its design life or maybe per year. The drainage coefficient is often assumed to be 1, but it will change. It can vary from 1.4 to 0.4. But you should remember one thing, that the effect of drainage coefficient is to increase the layer thickness and not the layer density. And therefore, if you foresee the problem of drainage in the field, it is always desirable to provide drainage system or maybe sometimes subsurface drainage system. These drainage coefficients are based on the quality of drainage. And quality of drainage can be excellent. There are 5 categories: excellent, good, fair, poor, or very poor. If the water can be drained from the pavement layer within 2 hours, this is the excellent quality of drainage. If it takes, let us say, 1 day, it is good. 1 week, it is fair. 1 month, it is poor. And water will not drain at all, then it is a very poor condition. Now, based on the quality of drainage and based on the percent time pavement structure is exposed to moisture levels approaching saturation, the drainage coefficients M2 and M3 are suggested in the AASHTO guide as given in this table. So if let us say if the drainage quality is good, that means the water can be drained from the pavement surface within 1 day, and the percent time a pavement structure is exposed to moisture level is less than 25%, then its value M2 or M3 is 1.15 to 1.0. But it can be as low as 0.4, it can be as high as 1.4. So that is how you determine A1, A2, A3 and M2, M3. And once you know it, you can find out what is the structural number. Say, for example, if you take one case where pavement is designed or the existing pavement has the following composition. You have a bituminous layer of 150 millimeter composed of AC and DBM. Below that you have the granular base course of WMM type, let us say 250 mm. Below that you have a sub-base layer of 250 millimeter thickness, and then you have a subgrade soil. Subgrade, you can assume 8% CBR. And let us say the modulus value of this bituminous layer is 3000 MPa. Base layer is provided with 100% CBR and sub-base layer is provided with 30% CBR. What is the structural number? The structural number here, Sn, is A1 D1 plus A2 D2 M2 plus A3 D3 M3. A1 you can find out from that chart which is given in the AASHTO guide. This is E value in PSI. So in PSI, 3000 divided by 0.007 will be 420,000 PSI, let us say. Corresponding to that, you find out what is the value of A1. This is 0.42. This is 0.42. So A1 is 0.42. D1 is 150 millimeter. Convert that into inches. So let us say 6 inch. D2 is 250 millimeter. That means 10 inch. And this A2 depends upon we are taking CBR as a parameter. So corresponding to 100% CBR, this A2 value is 0.14. D3 is again 10 inch and A3 corresponding to 30% CBR, its value is 0.11. 0.11. And let us further assume that M2 and M3 are 1. Assuming that there will be good quality of drainage and 25% of the time, or the pavement will remain in the contact of the water for less than 25% of the time. So M2 and M3, they are 1. So you put all these values, you get SN 5.05. This is the structural number of the pavement, this pavement. Now in AASHTO method of pavement design, if you know the design traffic life, corresponding to design traffic life, we find out what is the requirement of structural number. And then this structural number is converted into D1, D2, D3 by method of back calculations. And we will discuss this AASHTO method of pavement design also in our next session. So thank you very much for watching this video. If you have any question, you can write in the comment box.